think we can start. Thank you so much, guys, for showing up for the 5th lecture in this drenching rain outside. Yeah, so finally we are talking about one of the frontier language models. It was the frontier at least last year when it was released. We are talking about Llama3. So for those who are not aware, Llama is this series of open source models from Facebook. They have been releasing one nearly each year. This year they had the Llama 4 release. We are talking about the Llama 3, which was released last year from Facebook. This is an open weights model. And when it was released, this is nearly as capable as GPT-4, which was one of the SOTA models of those times. This paper is, so today we are like going down, reading the paper, seeing what is happening inside it. And there is a lot going on. Like this is a huge paper of like 70 pages, like not even appendix, just like 70 pages of content going on it. And something very fascinating about the paper is that this is a paper which talks about how Llama 3 was built, but this is also a data paper at its core. They talk a lot about data. Like the entire paper is basically how they massage data, which we know is like the most important thing. Having said that, the fascinating part is they have nearly no discussion about the pre-training data. So if you look through the paper, like the 70 pages of worth of like information, the pre-training data section is really, really small. And like nearly no details about where the data is coming from. All we know is like it's trained on 15 trillion tokens on the internet. What it is, where it comes from, what's the mixture, we don't have as much detail. But on the post-training side and everything after you do pre-training, there's so much information in the entire paper. And we'll go through the entire thing today. Yeah, so let's start. At a high level, there are like, this is the content for today. The paper is divided into 3 high-level sections. We'll talk about pre-training, which we have talked about in the past. We'll talk about post-training, which we have also covered in the past. And we'll also talk about how, once you have such a model, how do you manage to take into multimodal input, like images, videos, and speech. Because we know like today's frontier models can take images and different kind of modalities, and they also function on that. So we'll talk a bit about how once you have this pre/post-trained model, how you can modify the architecture without like changing too much about the language component to still like take into account the images and the video part. So starting with the pre-training section, we have talked a lot about pre-training in the past. This is the task of predicting the next token on the entire internet. At a high level, the paper has 4 different sections. We'll talk about pre-training data, which is not much. We'll talk about the architecture, and we'll talk about scaling laws, how the scaling laws that we have talked about in the past, how they actually use scaling laws to determine the size of the model. We'll talk about infrastructure, how it is trained, and exactly how it is trained over the 15 trillion tokens. Giving a bit more context, so because this is a large scale run, this was done over 16,000 GPUs, and the estimate is this was trained over 7 to 10 weeks roughly. So within 7 to 10 weeks, and the rough estimate is this, just the cost of cluster was $65 million for this single run of like GPT-3. Obviously excluding all the capex cost of like engineers, failure modes, etc., etc. And yeah, we'll go through like at this large scale training, things fail a lot. So one thing I really want you guys to take is like, yes, we have like learned a lot of concepts. We have learned like how things work, but once you like start combining these things together, once you like bring these things together, so this paper has like hundreds of authors, right? Like if not like more. What is happening across these so many people, right? Like this is not just like one code that you like start somewhere and you come back like 7 weeks later and okay, you have a checkpoint. That is obviously not how it works. One takeaway that I got from this paper is like this, like training a large frontier model is like in some ways a living organism. Like there are many branches, many things going on. So it's basically a fractal of details. Like there's so much details. There's one thing about learning the theory which we have learned over the last four weeks. But there's so much about like once you actually start training a model at this scale, there are many hierarchical details, and I think obviously those details matter. And like Llama or like Facebook did not have to like release such an amazing treasure trove of information. Like they went like into like, really extreme detail of like how every part functions. So I think like this paper is like a good introduction or like understanding how. And I'm sure things have changed in the last 1 year, but still like this is a really good take on like how do you actually train like such a large model at scale. Okay, so starting off like with the what we are doing today is we are like literally going through the paper, and I'll give you my takes as I was reading through it and different sections. So we have a lot of ground to cover today, and so okay, let's start with the pre-training. So the whenever like people train a frontier model, it's you have seen they have like different sizes. You have a large, a small, a medium, different things. So in this case, the biggest Llama3 was 405 billion parameter model, and we have also touched a little bit about context length. And you know, like from when you use ChatGPT and other things, the context length is the amount of information that it will take. In this case, the model can take 128,000 tokens, which is a lot. And we'll also talk about how once you're training something at this scale, how does it take this long of a context length. And also like how did they decide on this number? Like what is this 405b parameter? Like how did you come up with like this looks like a random number, but obviously it cannot be random, and it will be like derived by our scaling laws as we have talked about in the past. So that is also something we'll touch. So to start with, giving like a high-level overview, Llama3 15 trillion multilingual tokens. That means the token is not just in English language but also other languages, because Meta obviously wants like ultimately they want to serve this model across the world to different languages. So it's a 15 trillion multi-token training, which is like compared to Llama 2, it was like 1.8 trillion. So again, like roughly an order of magnitude more. The total amount of flops that went into it is on the order of 10 to the power 25, which is roughly 50 times more than Llama 2. Again, so this is you're scaling at work. They wanted to train a bigger model, so they had to put in more data and more compute. And like just a brief recap for people who were not present before in the scaling laws. When you have a flops or when you have like the total computation, it's dominated by only two factors: the total amount of data that you have, which comes from the total number of training tokens, and the total amount of computation, which is totally dependent on the number of parameters that your model have. So basically, the multiplication of these two things, in this case like 405b, in the largest case, multiplied by 15 trillion tokens, is how you like get to the total amount of flops. And we'll talk about like how do you exactly choose these two numbers. As I mentioned before, there are 3 high-level sections to it. The first is you have your standard language model pre-training. In this stage, you give it quote-unquote the entire internet, every single thing written by human out there. In this case, 15.6 trillion tokens. And in the first stage, also the most expensive stage, the model is just trying to learn the structure of human language. It's quote-unquote reading, as they said in the paper. Reading the entire internet, understanding large amount of information and knowledge from the internet, and trying to learn the structure of language. And in the second stage, in post-training, as we have talked about before, it's trying to both be a good assistant, follow instructions. So it has to like follow instructions, act like an assistant, be able to do very specialized tasks like people care about math, code, etc. So the second stage is mostly how do you align this to things we care about. Because after the first stage, as we know, it's just a next token predictor. It can predict the next token really well, but you cannot use it to do things. And in the second stage, we talk about different kinds of variety. Like for here you see, in the second stage, we care about code, math, different reasoning, long context, multilingual, not hallucinating, all of these criteria. How do you like, once you have a pre-trained model, everything which comes after, in the paper, the definition of post-training is everything which comes after pre-training. So anything which is like not pre-training specific will be post-trained here. And they use SFT, we have talked about SFT before, and they use DPO, which is a different version of PPO. It's a much simpler version. It's less RL version of PPO. I'm not going into details right now, but when you see DPO, you can think of like we are doing RLHF stuff. We'll have reward model and all those things, and we'll come to that. And the third section, once you have a pre-trained and a post-trained language model, how do you make it a multimodal model? How can it read images, videos, speech, for example? They have a similar pipeline, like all these three different modalities have a similar pipeline. I'll pick up images in this class, and we will talk about how once you have a trained transformer which can read text and do things for you in post-training stage, how you can add images later on without changing your model at all, because you don't want to like destroy or change the pre-training stages. So you already have LLM, you have a language model. How do you integrate images like post in the training? So this is like three high-level things that we are going to cover. Any questions? Yeah. Okay.
I guess I have a question about the multimodal aspect, because like human brain, for example, has like different modules to handle like speech versus vision and so
right.
on. Would it make sense to like train a natively multimodal model where you feed it like in addition to all the text like all of YouTube?
Yes, so they do independently train different encoders for different modalities. They're totally independently trained,
yeah.
And then they fuse it together. So you independently pre-train different modalities like image, videos, and speech, and then you find a way to fuse your language and the image modality together, and we'll see how this happens. To your question, from the rumors I know GPT-4 was actually continued pre-trained with images, so that is probably what GPT-4 did, but in this case they have a separate version. Any other questions? So to start with, so here we are, let's start with the pre-training data section. They mentioned that they use data set from variety of sources with the knowledge cut of 2023. That is the most information I have here. After that, they talk a lot about data cleaning and filtering, like removing PII information, personal information, using HTML and cleaning up the HTML because a lot of internet has like HTML pages. Doing different forms of deduplication because you do not want to like either memorize or overtly sample from one distribution, which is like on the internet a lot. And then another theme throughout the paper is, okay, there are like two themes in the paper. Because they had Llama 2 when they were training Llama 3, they use Llama 2 extensively for different kind of like classifiers, filtering, mechanism, etc., etc. And another big theme of the paper is synthetic data. When we talk about different cases of fine-tuning, they create a lot of synthetic data. And in some cases they use Llama 2, in some cases they use Llama 3. So they're training the model, and during post-training they're using a previous checkpoint of the model to get synthetic data to make it better. So it's a very cyclic loop, and we'll talk a bit about that. And obviously, another thing I want to note is that, so let's say you are like training this model, right? Like you are in the pre-training stage or post-training stage. How do you know something is getting better, right? For LLM research, it's mostly evals. You have evaluation sets across different benchmarks, across different categories. And all you're doing is you're trying to evaluate how good is this checkpoint. Can it how good can it score across different benchmarks? And because this field is a STEM field, right? A lot of these benchmarks are dominated by math, science, reasoning data sets. So we'll also see how different design decisions during training are taken to sometimes oversample math and reasoning data sets, because at the end of the day, the evals have to show higher score on these data sets. So that is also one reason we'll see how code reasoning and multilingual will come again and again, like during the entire process.
I found it just above in the text extraction and cleaning, really interesting how they handled the alt attribute there.
Yeah, you can.
So like, I guess they say a lot of the mathematics online is the formulas are in images, and so they explicitly like train on the alt text so that they actually get the formulas. Like it seems like tricks like this might be like you're saying improve the benchmarks.
Right. So on the data set, like continuing on the data set, one thing that they said here is that they trained a classifier to categorize different web information into different categories. And they mentioned that because the internet is oversampled with arts and entertainments, they use classifier to downsample it because it's overrepresented on the internet. So this is also another interesting bit that I found. So there's another thing that you want from a data set is like how good is a data set, and is there a way to determine before your training is like the quality of the data set? They have two different ways they do here. The first one is scaling laws for data mix. What they do is they take a previous checkpoint or like smaller models and mix different data mixtures. And because you can train smaller models on different data mixtures, you can find out how good a data mix is, or like how good a data mix for the biggest model would be. Because at the end of the day, I think a lot of this paper is about the 405B, because the smaller ones they can train, like the 8B or different sizes, they can like retrain different sizes. Just a second, I have another point. Another way another theme of this paper is this thing called annealing. Annealing is the idea is that when you are at the end of the training, when you're done, when you're like close to the end of the training, you can actually do different kind of design decisions, because it is during the end of the training, like during the last 1% of the training, is when the final information is being locked in the model. So we'll come about different kinds of annealing they do, but this is one example of like they use annealing to assess the data quality mixture. What they do is they take the Llama 8B, which is half trained, so they take the 50% trained checkpoint, and from there they decrease the learning rate to 0 over the next 40 billion tokens. And at this point, like half trained Llama 8B, because they already have it, you can like add different data mixtures at this point and like decrease the learning rate to 0, so like basically lock in this information and see how. Also the new data that is coming is only 30% in weight, so 70% your original mixture, 30% is what you want to test, and you can at this point test different kind of data mixtures and see, because you're adding this 30% new data, how good are the downstream benchmarks. So like during the, because right now you already have your 405B in training and it's not finished, and you want to like decide, do we change the data mixture during the end of it? Your 8B is already finished, you have the middle checkpoint. You can do different kind of ablations. Ablation mean different kind of A/B testing, where you like try different mixtures and see, okay, for my biggest Llama 405B, which mixture would be good for like a smaller scale model, and that could be like, we can just like take that mixture for a larger scale model. And this becomes much less computationally expensive compared to scaling laws, where you have to like train many different checkpoints. So yeah, this was another interesting bit I found. On terms of annealing data, as we said, because at the end the benchmarks care about code and math a lot. During the last, literally during the last, I think, I would say some millions of tokens, like probably 40 to 60 million, I don't exactly remember. They start adding code and math or like high quality benchmarks. And this is like now coming in this mid-training regime, where before you're done training, you can like start adding different kinds of like data set which will help your downstream benchmarks. And because you want this model to like locked in within like a good math / code model, you start adding like higher quality mixture right when you're decreasing the learning rate to 0. That is like at the end of the training. Yep, you.
Yeah, so when you said like there are scaling laws for data mixture, the y-axis is still the ordinary regular laws.
It's still the ordinary regular laws.
And when they're annealing, they're using on the y-axis benchmarks, or they're still using laws?
It's still the laws, but I'll show one example where you can also have benchmarks on the y-axis. That is right when we like go to the scaling section. Yeah.
We only do annealing on the 8B. So they use the 8B to tell them what good data mixture is, and then they just transfer it to the larger model sizes as well.
Yeah, I mean this is the only paragraph I have. So, although this is a really, I can share the paper later, but this is a really great paper from, I think, I don't remember, but this paper talks a lot about different data mixtures and how can you like select a good mixture, and I think this recipe was from the paper.
To what extent do you think this leads to overfitting?
I mean 8B, for the downstream task. So they specifically mentioned that they do not use any of the downstream benchmarks. like they're using high quality mixture, but they're like explicitly saying they don't use like downstream benchmarks to actually anneal. Like they evaluate on the downstream benchmarks, but that data is not part of your annealing mixture.
Yeah, so you would dissect that.
Yeah, any questions on the data?
Sorry, what's annealing quickly?
Annealing is like when you are at the end of this training, like so you're training on like 15.8 trillion, right? Let's say like on the 15 trillion token you have like still 800 billion tokens to go. You can start changing things, like you can start changing the data that you're showing to the model. You're still doing the same task of like predicting the next token, but you can start changing the kind of data you're showing. So in this case they say that, oh, if you start showing high quality math and code data, as in like you save it for the end, for the very end of the training, you get a model which is like much better at math and code. Or there are other things they do for annealing, as in like you can like start increasing context length during the end part of training. So the model that you have, the last checkpoint, can actually handle large context lengths. So there are like different things that you can do during the course of training, and annealing is just the phase of like at the end of the training how you like change subtle things about the input.
So it's not like a mathematical change, just a change in the data mix?
Yes.
It sounds like what they're saying here is they like cut it off early, basically, right?
What do you mean by cut it off early?
Like it says they set it to 0 on 40 billion tokens.
No, this is specifically to test the quality of data mixture.
Yeah.
But also on your actual model, you'll anneal. You'll eventually anneal on the bigger model, because at the end of the day, the bigger model is what you care about. And yeah, this is just to test how good a data mixture is. Yeah.
You said you want to lock in on like tracing capability, so would you bump up the learning rate on those tokens relative to like the mixture you had previously, or you still decay the learning rate as you were decaying?
Yeah. So annealing, I think specifically you actually go to 0. That is the point. Like during the very end of the phase, I have a diagram to show that actually. So this is how the learning rate changed for this particular model. At the very starting phase, the warm-up phase, you go from 0 to the peak learning rate, and it happens in like a few million initial tokens, and then you have this slow gradual decay throughout the entire course of training, which is a cosine decay. And finally, at the very end of the training, you basically decide to go back to 0. Like you set the learning rate back to 0. And that is where you can like do different kinds of things, and that is the phase where you do annealing. For example, another case of like how okay, we'll come to this. We'll touch on this later again. So moving on to the architecture section, the very first line is Llama3 uses a standard dense transformer architecture from Vishwani et al. 2017, and this is the same architecture we have studied before. They do make small changes, but again, it's a testament to the original architecture that it still remains the same like 8 years later or like 7 years later. And one thing that they note is like our performance gains are mostly primarily driven by data quality and diversity, and also increasing the training scale. So this goes back directly to scaling laws, where having a better or a more bigger data set and also training a larger model gives you like most performance gains. Having said that, there are a few key architecture changes. I'm not going into detail right now, but we talked about attention before, and we talked about how the attention worked. I can briefly pick that up and yeah. So if you guys remember this photograph, what we're doing here is that we were creating these three different embeddings for each token. We had a key query value, and each query was attending to everything from the past, and this is like your standard attention. Since then, there have been like many different proposal to this approach, primarily to reduce the memory, and there have been like proposals like grouping different keys or and like a lot of these improvements are both to have efficient training, but also primarily to have efficient inference, because once you are serving these things, if your prompt is really big, these embeddings can become really big, and you have to like store them in the memory. We have not talked about inference much, so I'm not going down the rabbit hole. But most of the changes that you see along these paths is how can you like maybe don't have a single query. Maybe you can like have multiple tokens can have one query, or you can like group different kinds of query together. And this is one thing that they do is like they use this thing called GQA, group query attention, which is again just to have an efficient training, but also more importantly have efficient inference. Other things like when you put an attention mask, we learned before that you set everything in the future to 0 because you don't want to cheat, obviously. What you can also do is also put attention to things coming from a different document to 0. So let's say you have a Wikipedia and your context window is 8,000 tokens. But if you don't have 8,000 tokens from your current document, and you have document tokens from another document, you probably don't want to pay attention to that because that don't bring any value to this current context window. So you can like decide how to like make masks which are document dependent, where your document is coming from. They also increase the vocabulary. This was, I think, a very big increase. I don't remember the vocabulary of Llama 2 though, but Llama 3 it increased to 128k, and previously we talked about how GPT-2 was like 50k and stuff. And also like a bigger vocabulary also helps you lower the context window if you think about it, because now like let's say a word understanding, maybe previously understand and ing are 3 different tokens, and if you have a bigger vocabulary, understanding is a single token. That means you can fit more in the same context window. So that is also another reason why you want to like increase the vocabulary size, so you can like fit more things in your context window. That also means that your final layer, which is our final. Yeah, the because we have a larger vocabulary size, our final projection layer, which actually computes the final final distribution over each token, that matrix also becomes bigger. So we also have to take into account like how things change.
They also increase they 3 times increase in the dimension.
Oh, I did not notice that.
Llama 2 is 5,000. That's a huge step up. Isn't
You
it?
mean this one, right?
Yeah.
Right. So this would be primarily determined like this is a determining factor of like how big the model is, right? Yeah. So as before in this photograph, right, we have these embeddings flowing in, and one thing to note is like across, with one caveat, across the entire stack, the dimension of this embedding remains the same. When you have multi-headed attention, it decreases by the number of heads you have, but more or less you can like for a conceptual point of view, throughout the entire transformer layer, like through the computation and the communication layers that we talked about before, the dimension remains the same. And if you think about it, like how do you determine the dimension? Like all your linear layers or all your matrix multiplication then will be like d cross d, like this dimension cross the output dimension. And if you remember from like this diagram, there are only like 2 things happening. Like there's the communication step happening and the compute step happening. And if you increase the dimension of your input, that means all your matrices become bigger, right? Because all your matrices are basically d cross d, apart from the compute one, which is d cross 4d. So in a way, the input dimension to your entire model is the only determining factor for your total amount of parameters in your total model. So these 2 things are like strongly correlated. Like if you choose a larger dimension, you'll have a bigger model. In fact, like I would say, like to first degree of approximation, this is the only factor which will determine like how big your model size is. And I'm going to talk just in a second how do you actually arrive at like how do you actually choose these numbers, or like how are you actually arriving at this size. Yeah, before moving on, are there any questions for the architecture section?
Are we going to cover rope at some point?
I would love to, but we only have 1 class left, so we'll see. Yeah, I wanted to cover it today, but there was just so much ground, so I could not touch on it.
Is sweet glue now the default activation function that one should use?
As far as I am aware, yes, but okay. So moving on to the second, to the scaling laws part of the equation. So just giving again a brief recap of what scaling laws are for people who were not here before. what we have noticed when we started training large language models is if you have a larger model, you can guarantee a lower loss. Not just that, you can actually guarantee a log linear scaling, as in if you increase the total computation put in a language model by roughly an order of magnitude, like roughly 10 times, you can like see the loss decreasing by half. And not just that, what we have noticed is that across many orders of magnitude, like as in like you train a very small model from like a few million scales to all the way to like multi-billion model, what you notice is a very strong correlation of the loss decrease. Something like this. So on the x-axis, what we're looking at is the total compute or the total floating point operations that you spend. And as I just mentioned, it's a product of like two things: the total amount of data that you have, which is the total number of tokens, and how big the model is, right? So as you notice here, like across several orders of compute, like from like 10 to the power 20 to 10 to the power 25, like across 5 orders of compute magnitude, what you notice is a very linear decrease in some form of loss value. I'll talk in a second what this exact metric is. What that means is, once you're actually about to start a 65 million training run of like 16,000 GPUs across many weeks, which is a lot of money, you need to be like very confident beforehand of like how much data you want to train on, and also how big the model has to be, right? And how do you do that is like you train many smaller models at many small scales, and at different scales you notice, okay, this is the ratio of my data versus my model size, and this is the best loss I'm getting for different kinds of different points on the x-axis. And based on that, you can actually extrapolate how good a future model would be, which is again like it's really mind-boggling. Like if you think about it, like this photograph, they trained models from like 10 to the power 20 to 10 to the power 22 flops, and these are all the models, like all the small models they trained, and eventually they just linearly interpolated it, and 3 orders of larger compute scale, they were able to predict the result of an experiment before even starting the experiment. Like it's very mind-boggling to me. One thing I said before in the scaling loss paper is that what you are predicting is some form of loss value, not the accuracy of some downstream task, right? Like how do you know that even if you have a good model, good loss, will your downstream task still follow a good pattern? In this paper, they also predicted accuracy on some downstream tasks before even training the model, which is insane. And I'm just talking about like I'm coming to that in a second. Okay, so how do you actually do that? Let's look at this plot. This is a plot it's called an isoflop curve. What that means is each curve that you're seeing for different colors use the same amount of compute. So once you fix the compute budget, let's say you fix like this compute budget of 6 to the power 18, right? Now you have 2 different axes to change, right? You can change how big the model is, or you can like train on more data points. And what you get is like something like this as a smooth curve, where when you go on the right, you have more training tokens, as in you're training for more, like you're training for longer, but you probably have a smaller model because you have to like fix the compute, right? And what you notice is like, again, there will be a sweet spot. There'll be a sweet spot between like, what is the total amount of tokens should I train for, and what is the model size? And you can do this for many different different compute budget. So I think a good lens to see this is like you predefine a compute budget, as in you predefine this many GPUs for this many hours or this many days, and like probably for this one it probably would be like 10 minutes or like an hour maybe. For this one it might be probably a few days, and then you want to extrapolate it to like 3 months or like 2.5 months. And what you notice is a very smooth scaling across the thing. So this is the same graph. On the right we see the same graph as the left graph. We have just flipped. On the x-axis we chose now the compute flop, which are these models, and on the y-axis we chose the best validation loss. We chose the model which is the best loss, and we see that from 10 to the power 19 to 10 to the power 22, you see a very like nearly straight linear plot. That means if you keep scaling this line, you can actually reach 10 to the power 25, which is so this is what they decided beforehand. Maybe they decided we have like 16,000 GPUs, we have like maybe let's say 2 months of compute budget. What is the best we can do? This is the question that they start with. Is given this amount of compute for this amount of time, how do we decide the right architecture size and the total amount of token that we should train for? And the answer is here. Like we basically scale this up, go to 10 to the power 25, find out the total number of training tokens. In this case, it was 15 trillion, which is exactly the one they use. And you find out exactly what, once you know the training tokens, you can find out like the model size from that one. And that is how they found like 402 billion parameters. But they ended up choosing 405. They noticed that when you have when you actually go to like larger compute budget, these plots actually become more and more flatter, which means they're more robust. They're more robust to like slight perturbations to like total number of tokens or total compute. So they ended up choosing like I'm sure they decided like the embedding dimension first, as you mentioned, and which ended up deciding the entire architecture, and that ended up deciding the 405p scale for the model. Yeah.
The depth, it's also linear in the depth, right? So can't you add like a layer or two to make it exactly the number you want? Or?
I'm sure there might be a way to make it exactly the number, but from what they said in the paper, they didn't care much at that. Yeah. A few billion parameter was nothing at that. Yeah.
So on the previous scaling plot you showed, they were able to actually test to see how close they were to the target on the loss, right?
Yes.
But is it correct to say that on figure 3, we don't know where the 405B model would lie?
We would, right? Because this, you can extrapolate this and you can like know exactly the loss value.
But we only got one. Oh, you know
Figure
the loss
3
value.
is they control both sides of it, right?
So this was like they were trying to
There's
find the
no need
total number of tokens.
Yeah.
Is like what is the optimal amount of tokens that we can like train for this compute budget. But I'm just coming to the loss bit as well. I'm coming back to the next figure. Any questions before that? Okay. So now they also wanted to predict accuracy on some downstream task, which was very fast. Like I've never seen this before. Maybe this is common practice, but I was not aware of it. So they had a task. It was, I think they used the ARC task. I'm not sure if it's the same ARC AGI task that we know of, but some downstream task. And what they wanted to predict is, can we like predict the accuracy of the model on some downstream task before even starting the training run? What they did was they made this plot. So what is this plot? You compute something called as negative log likelihood loss, or like in simple words, this is also perplexity or the surprise in the right answer. So because you have a downstream benchmark and this benchmark has right answers, right? What you can do is at all these different models, you can see how surprised the model would be looking at the right answer. You can like compute the log likelihood of the final like the right token at the final layer, and you can average it out for the right answer. And what you notice is that obviously a larger model, more compute being spent, you'll have lower surprise. In the best case scenario, you have zero surprise, right? You know exactly the right answer from the downstream benchmark. But obviously we are not in the best case. And what you notice is this again, this linear scaling as you increase the compute budget. Notice it's log linear scaling because x-axis is log vector. And once you have and because you already have all these models, right? You have all these models, so you can actually compute the accuracy. You don't need just you don't just have the loss. You can also compute the accuracy for these models on this downstream because you already have these models trained. And that is what they did. They computed the accuracy for all these smaller models, and they also had the Llama 2 models lying around from last year. And they computed and they knew the exact loss value for these Llama 2 models from last year. And they computed all the, they plotted the loss to accuracy graph for Llama 2 models. And they noticed, they fit a sigmoid curve to it, which kind of makes sense. Like because once you're reaching accuracy 1, you'll start seeing diminishing returns. And what they predicted was this value here. So they predicted like some loss value and like some accuracy, and this is the true value of the final prediction. I think it was slightly higher than the prediction, but again, like this is just the testament to scaling laws. Is before training a model, you can predict accuracy of on a downstream task because you have like smooth graphs showing up. Yeah, so this is exactly how scaling laws was used in 4OB to like both find out the total number of tokens, find out the size of the model, find out like how good it would eventually be. Also, just as a reminder, I think I've noticed, I have mentioned this before. OpenAI, when they train their base models and when they train larger models, recently they trained a bigger base model which is 4.5. They also have in-house eval set like this, which is their own code base, which is the code base trained for GPT-4 or like GPT series of models. And because that is not on the internet, they use it as a hidden test set or a hidden benchmark to keep evaluating how good the perplexity could be. Yeah.
Are these scaling truths considered like or scaling laws considered fundamental truths of like transformer systems? Like, is this something you just stumbled upon, or?
Yeah, I think I mentioned a little bit about on the scaling. I mean, we do call them laws, but I'm sure this is not a fundamental law of our universe, right? But I'm sure it is a fundamental law, not a fundamental law, but this is definitely an artifact of both deep learning and the kind of data we are training this on. Because we have seen again and again, this holds not just for transformer, not just for text, but across different modalities. Recently, Waymo showed that scaling laws hold true for like their prediction system for, which is a very different modality for self-driving input and very different architectures. So we can say this holds for deep learning in general at large scale, and people have showed this agnostic to architecture and the kind of modality that is coming in.
Interesting.
Any questions for this part before we move on?
When do you think we'll let all of data
I mean, that's a very ongoing question since last year, and a lot of people have been talking about when will we run out of data. Different labs have different answers, and I'm sure they're motivated by what they're doing. Having said that, I feel like we have already started to see diminishing returns from larger models. Like GPT 4.5 was arguably 10 times bigger than 4. Rumors are they wanted to name it GPT-5, but it was not good enough, so they had to name it GPT 4.5. And they also deprecated it after a few months. I think it will be deprecated soon enough from like the chat. I think it has been from the API, but I'm not sure. But yeah, so we are already seeing diminishing returns from the internet, and that is where all the reinforcement learning stuff that we talked about previously comes into picture. Is there a possibility that you can still use the large scale web data, but probably with a different loss objective, or probably like how we talked about, maybe some things like some hard math problem you need multiple passes, a different way of ingesting the same information that you have. So I'm sure people are already coming up with like new interesting ideas to like still use our large scale web internet but in different ways.
So it sounds like compute is still currently the limit, because like it's the data and compute is like.
Yep. I mean, compute is like people are like still spending. Like for example, Grok 4, which was released last week. I was very shocked looking at it. Like in Grok 4, they mentioned that they use the same amount of compute in post-training as in pre-training, and this was like unheard of before. At least like no one has reported this before, because we just saw like how much compute is spent in pre-training, and post-training used to be like a few million to a few billion tokens. And like now being able to like spend as much compute as in pre-training and post-training is a huge thing. So I'm sure, and we are already seeing even diminishing returns from that. So yeah, I think this year, next year will be like really interesting, and like how people actually end up spending a lot of compute. Having said that, I think there are also many other accesses. Like we saw in the recent Kimi paper that having a different optimizer changes things a lot. Right, because all of this is still Atom, and we are starting to see newer optimizers being used. So I'm sure there are other accesses where we can still use the same data in a much more efficient way. Okay, I'll briefly touch on infrastructure because we have not talked a lot about that in the past. Yeah, so as I mentioned, Llama 3 is trained on 16,800 GPUs across 7 to 10 weeks. And there's so much dense details in this paper to go over. I'll go over like very small details. For example, one thing that we have not talked about a lot is once you have such a large model, right? Once you have like a 400B parameter model, and once you have like 1600 GPUs, how exactly is the training happening? Like at some scale. So these GPUs, like the best of the GPUs, you have like 80 gigabytes of like GPU VRAM. So at some point you cannot like fit your model, let alone like fit the like even one batch, do a forward pass, backward pass, right? So at some point you have to think about parallelism, like how does parallelism actually works? And there's so much detail to like this could be an entire lecture, and maybe it will be. But there are like 4 axes on the parallelization scale. One axis that I can show briefly is called tensor parallelism. This is like when you actually have a really large model which cannot fit on a single GPU. How do you actually break up the model? And you can like actually break up in like 2 different. So again, what do we want to do? We want to like matrix multiply, right? What happens when your matrices don't fit on a single GPU? You have to somehow break the matrix, right? There are 2 ways. You can like either break it horizontally or vertically, right? And that changes the dynamics, because if you have a half horizontal matrix on one end and a half horizontal matrix on a different end, how do you actually do the matrix multiplication across 2 GPUs? And it changes a lot if you do it vertically. TLDR, in one way you have to concatenate the answer, in one way you have to add the answer. But that just to say that is one way how you shard the model across GPUs. Just to say a little bit about GPU, usually you have one node, and each node roughly has 8 accelerators or 8 GPUs. So this is like 8 GPUs tightly packed together. But then you have many nodes in your entire data center. And the dynamic also changes when things are divided across GPUs on one node versus when the model is across many GPUs. In some recent papers, people also had model training across data centers, which is insane to think about. Like across data centers, imagine doing a forward pass and gradients being flown from like data pass. Oh, okay. There's also another new thing when people are also exploring with heterogeneous computing, where if you have different kind of GPUs or even not GPUs, how do you train a model at like in world scale level, as in like many people across the world have machines, devices. Can you train a model heterogeneously across the world? That is also something people have been exploring. But in the simplest case, we have a single kind of accelerator, in this case either a GPU or a TPU, and you have many more of them, 16,000 precisely in this case. How do you shard this? How do you parallelize this? How do you split this? So this is an entire literature on its own. And there are like 4 main axes how people shard this. And yeah, the paper goes a lot into like different axes. So these are like the 4 different dimensions of like, so one of them is data. Obviously, if you have like different data batches, you can like pass different shards of data to different model, like how the model is seeing. Another one is called pipeline parallelism, where imagine your model has 8 layers, right? And one of the node has 8 different GPUs, right? You pass in the first data batch, it goes to the first GPU. At this point, the rest of the seven are empty, right? They're not doing anything. This guy can go to the second one, and if you let it like finish the entire forward pass, at any given point of time, 7 GPUs are ideal, right? Which is really bad for your thing. What you can do is like something like factory. Like in a factory, you have pipelining. If you pass in the first thing, and as soon as it goes to as soon as it passes the second thing, you can like pass it another data point for the first GPU, and which is what is shown here. Like this is how things flow in a pipeline fashion through GPUs, and they have their own problem, because at the start there will be a time when 7 GPUs are idle. These are called bubbles, and people talk a lot about how to solve bubbles next time. But yeah, I'm not going into any of these details, but just to be aware, when you have to actually train a model at large scale, you have to like think a lot about how you're parallelizing things and how you're like, also speed becomes a big bottleneck, because if you are on a single node, these 8 GPUs are tightly linked. You can actually communicate things across them really fast. But once you have like things across different nodes, across the data center, you have to be very mindful of what you are actually communicating across nodes, because that communication becomes your bottleneck compared to the computation that is actually happening on the GPU. Another amazing graph that we got in this paper was all the failure modes, because now when we are at like 16K nodes, things will fail. Like it's like at 16K nodes, if you're training over 7 or 8 weeks, one machine or other is bound to fail every day. And obviously the most common failure case is faulty GPU. Like there would be like one failure connection somewhere, and that leads to like the 30% of interruption. But also like other very funny things, like for some reason they mentioned that they had every single day they had like Linux upgrades, and one of the machine will like go down, which is like, yeah, it's really frowned upon on this like Llama 3, but they had like someone upgrading Linux every single day, and like they had a guy there managing the cluster. Other things like server chassis had like 2 problems. I don't know what was happening there on the server chassis. But yeah, many very different, like at this large scale training, even very small minute things can like actually end up like stopping your training. But yeah.
So when you're training, how often do you like save the checkpoint somewhere like off the GPUs before, like?
I'm sure they're like storing quite frequently because things are bound to fail, and you. So this is something which comes up often, is like, and people like brag a lot about this when they actually solve it, is like really clean logbooks. As in, are you like, is your pre-training team at a stage where they can have like 0 restarts or all automatic restarts? For example, Kimi2 paper, which I just talked about, showed they had like amazing graphs without any failure modes. So I'm sure as we are like learning more about optimization literature, other literature, or even like managing failure modes, PyTorch recently released, and they showed that how in newer PyTorch they can do automatic restarts for like some of these cases. But yeah, I'm sure the checkpointing save like that has to be a very frequent thing because you don't want to lose progress. And in here they mentioned that despite all these challenges, including like all the Linux upgrades and stuff, they were able to have like 90% effective training time, irrespective of whatever things like this were happening across. And yeah, with at least one training interruption happening daily for their run. Other very surprising thing in the paper is that temperature fluctuation throughout the day also impacted things. In this here, they note that even 1 to 2% of variation throughout the day, midday temperature was higher. That meant the GPU had dynamic voltage and frequency, so that impacted things a lot. So I'm sure during days when you have a higher temperature, things are bad for you. And also there was another interesting thing here. Oh yeah, they mentioned because they have these tens of thousands of GPUs where they all like suddenly, because imagine the forward pass happening, and then there's a collective communication step of collecting the gradients. At that point, the GPUs are not doing the computation. So suddenly the power fluctuation drops. And then you have to do the backpropagated, and suddenly it has to increase the power fluctuation of the entire data center. And they mentioned that, yeah, because during this collective phase, that was another big challenge, and they're still like trying to handle that. Like because it stretches your entire power grid, when suddenly like the power is like coming for like all your 16,000 nodes at the same time.
So, like in this Colossus cluster, like Elon Musk has these giant batteries from his gigafactory just to smoothen out the power. So when the power consumption drops, like he dumps a bunch of electricity into the batteries and like it's ginormous. It's like having like dozens of just trailer-sized batteries outside the gas power plant.
Interesting. And I think we are seeing news these days of like the Meta super intelligence team. They are like, I think Mark Zuckerberg's initial plan was to like take the next few years to build a really big data center, but I think they changed the plan looking at like XAI's progress in the last year, how they like spun up a large scale data center from scratch. And I think Meta is doing the same thing, and apparently it's going to be a Manhattan sized data center to train their new model, and I hope they're really good.
Hope it works.
Hope it works, yes. Okay, so that is all I have for infrastructure. We are we are halfway through the time, but okay, I'll quickly cover these through and then we can take a short break. The last part of the pre-training stage is when you're actually pre-training this model for like your 15 trillion tokens. They have 3 different stages. So more specifically, an initial pre-trained stage, a long context pre-trained stage, because your final model is 128K. But you throughout the training run, you actually do not want to train on 128K token window. 2 main reasons. The first and more important reason is that remember I mentioned that the biggest bottleneck is memory, and even more specifically the attention matrix that you have to form. And if you remember, like from the last lecture, like the previous lecture, the attention matrix is basically every query paying attention to every other key. So the size of this attention matrix is context length cross context length. The size of this attention matrix do not depend on the model size at all. Like this is totally independent of what your model size is. It's totally dependent on what your context window is. So if you have like 128K token, the size of this matrix would be 128,000 cross 128,000, and no GPU in the world can actually fit this large of a thing. And there's a lot of research done in like how do you actually like manage this large matrix, because this is the biggest bottleneck in terms of memory. So when you're actually doing pre-training, you do not want to actually train on a large context window. So what people actually do in practice is they train on a smaller context window throughout the entire training run, and during the end of the phase, I'll show exactly how, you start increasing the context window slowly and slowly and slowly. That saves you a lot of like both computation but also memory throughout the training. And I think second other reason is that you don't have data lying around throughout the pre-training run, which is actually 128K context window long, right? Like most of the data on internet do not have things to do across 128K context window. Sure, you have books lying around, but like still, most of the data will be within very short context window. And finally, as I mentioned before, at the very end, within some hundreds of millions of tokens, you start doing annealing, where you start changing the data mixture to for the model to behave in a very different way. I made a graph to demonstrate this. Yeah, so in this graph, you can see so on the x-axis we see the training run, which is in trillions of tokens. At the end, you have the 15 trillion token, and on the y-axis is the context window of how large the context window was. Initially, like for a very short amount of time, they actually start with 4K token window, and then they mentioned this is for stability, because initially you just want the run to start off like so for stability purposes you start with 4K, and at some point you actually double the context window and you start training 8K. After some point they also doubled the batch size. So just to reiterate, the batch size is basically how many elements you are processing in parallel multiplied by the context window, because like how many tokens you're processing in a single forward pass. So if you have 8K context window, and so roughly the batch size are in like roughly millions of tokens. Again, in LLM world, batch size is mentioned in number of tokens, not the actual batch size. So it's the exact like the big matrix that you have. So the number of the context window that you're training multiplied by how many elements you're training in parallel. Yeah, so at some point they decide to double the batch size, because obviously if you have a bigger batch size, you can like train faster and stuff. And that remains stable throughout the entire training run until you reach like some 14 trillion tokens. And at the very end, you start increasing your context window, and they do this in six stages slowly. So you go from 8K to 16K, and slowly you eventually go to like 128K. They did not mention what data they are using for this, for increasing the context window, because I would assume like you need some long context information for the context window. They, however, do mention when we talk about SFT and like post training, they do talk about how 3 different ways they find this long context information. And again, at the very end of this phase, you have this annealing phase where you start to add math and reasoning tokens because you want the model to be really good for math and reasoning. Yeah, I think that is all. Oh, another small thing. When you're actually increasing the context window, you want to make sure that the performance on smaller context window do not degrade. So this is what they mentioned. We successfully were measuring the model performance on short context evaluation has been recovered completely. So I'm sure as you increase the context window, as you double the context window, maybe your model gets worse initially, and you keep like training at that context window until it has recovered the performance as it was on that short context window. Another evaluation which was a very simple and dumb evaluation back then is this thing called needle in a haystack. This is like how the name sounds. You throw in a bunch of information together, maybe like 10 different Wikipedia pages, and throw in a random fact in there like I love chocolate ice cream, and you ask the model, hey, which ice cream do I like? So this is like one very simple way to like test can it actually process all the information to find this one needle in this huge haystack. And they mentioned this is like two things how they were like being aware of like how to increase the context window.
Can you give an intuition for what it's like for the model to adapt to the increased context length?
Right. So this is a really good question, and there's a lot to say on that. I think the biggest barrier to a larger context window is positional embeddings. And because I've not talked a lot about this, I cannot go down the positional embedding route. Okay, now because you have this question, I want to actually talk about something in this architecture. Okay, I have a question for all of you guys. So this is the transformer architecture we talked about, right? In the input, you have a context window of 5 tokens, and you have an embedding stage, which is a lookup matrix, and then you have like this 2 alternating phases of like communication and compute. And we talked about how in communication we create these key query values, and they take dot product attention, and then you have another thing which like converts this to a different embedding, etc., etc. I have a question in this. I have a question for all of you. Is like, what in this entire architecture is determining your context window? Like, where is the context window hard coded? Like what? Because you have a really good question, right? Like what? Like when you actually change or increase the context window, what changes? Yeah.
It's the attention.
Is it? Because attention is a weighted operation. It's a weighted average across a set of inputs, right? A weighted average across a set of inputs is agnostic to how many elements are in the set. So
But the operation of computing it?
Okay, let's go to the attention. So this is the attention operation, right? Just to clarify, all these linear layers are the same thing. We don't have like 128k different linear layers for each token. That would make no sense. We want to process each token by the same linear layer. So all these linear layers are basically a copy of each other, right? So in theory, I can like make this instead of like for example, when you talk to ChatGPT, if you give like 5 tokens or 10 tokens, it still works, right? It works on variable number of input. That works because what happens is like each linear operation creates key query values, and what you do is a weighted average, right? Attention is basically a weighted average, and the weighted average is basically done. It is a set operation, right? It's done on like some inputs of set, and because in average you take a sum and divide by total size, all of this is agnostic to how long your context window is. So where exactly is context window in the picture? Like why can't you train a model on like 100 tokens and like do a like 100k context inference or something?
I mean, the MLP does depend upon.
Nope, it does not. Let's go to the MLP.
Oh, I guess it's embedding times embedding.
Yeah, this guy is simply taking the same embedding dimension and getting with the same embedding for each token. So the MLP is also independently happening for each single token position. The MLP does not depend on the context window.
I guess it's just never seen those positional embeddings that far back.
Yes, exactly. So it is only the position. So it is actually on me. I have not gone down the positional embedding rabbit hole because it's a big rabbit hole. But now that we are actually touching on it, okay, because we mentioned, right, this is a set operation. Set operation is very like a very bad operation for language or something which has inherent positional structure to it, right? And like set operation basically it removes the position of the things, right? So what actually happens in practice, and according to me, this is the weakest link in the entire transformer architecture. Probably right down there with the tokenization. But yes, this is a really weak link, and since the first paper, there have been many different approaches of like how to hard code positions, and because the model during training has never seen a position saying this is like 4001 positional number, it cannot know, hey, what do I do when I get a new positional embedding? And there have been solutions how to like go around it, and there are many different things. But yeah, what actually happens when you actually increase the context window is both it has to learn this newer positional embedding, and people have made very different like solutions to like have length agnostic positional embeddings, or like can you train on smaller model, do inference on larger context window, but it also has to somehow see the large data, right? Like the data, if you're training it only on 4K context window and it has never seen books before, and you ask it to summarize books, it becomes just a harder task. It has never seen that data mixture. So again, from architecture point of view, apart from positional embedding, nothing in there is actually defining your context window. It's only how you treat positional embeddings and also the kind of data that it is.
What is a positional embedding?
Okay, good question. So here, let's go back here. So this was our starting point of the journey, right? When we actually take in words of text, we tokenize them into small words, and then we make this thing called embeddings. This was from a lookup matrix. Now there are different ways you can like think of like how do you assign positions. A simple way could be you just number them 1, 2, 3, 4, 5, 6, 7, right? And you like probably add the number in here. That's one solution. There are many different solutions. There could be a different solution where how about you like fix some random embeddings for each position, and you maybe concatenate them with them, or maybe add them with the embedding, right? So every time the model sees this word and it sees this embedding, it will know, oh, this embedding always comes from the first position, which is again a very hacky way of thinking about this. But yeah, again, this is a big rabbit hole, and I have not touched on it yet.
But this is something about like learnable. Like why don't we people?
We have also tried that. There are many papers on like, can you? Oh, by the way, this matrix is learnable. So when you actually get the gradients back, you're also tuning these embeddings. So even if you set random embeddings in here, you'll actually get gradients back, and they will be like trained.
Wow. So during the pre-training of this model, they're learning the embedding matrix also.
Yes, you always learn the embedder. This was something I was very fascinated when I first realized. Oh, they actually, so if you actually go and see these embeddings, they have meaning, they have structure to them inherently. Yeah, because they're also like passing in the gradient.
When I trained Llama against the embeddings, it's suddenly just taking up like 50% of the model.
Like for KB and stuff, is the positional embedding learned or
small?
Now they use rope, which we can open it up. It's a big blocks. But maybe this is a good time to take a break. There's so much more to cover, and I don't have enough time. But maybe we can take a 5 or 7 minutes break, and we can come back after it.
So yeah, like the crazy part was.
Guys.
For me, is it would be like separate.
Okay, so I think we should continue. We went through. We went through the pre-training. Now it's time for post-training, and I think we have like spent 2 lectures on talking about post-training, on how you do SFT, supervised fine-tuning, how you do reward modeling, and how you do RLHF. And yeah, in this we'll see how it's actually done in practice. Do I have anything to talk about? Okay, this at a high level, this is. Okay, just a brief recap for people who were not here before. When you have done the pre-training, you have this model trained on like 15 trillion tokens in this case, which can like predict the next token for everything. But it is not useful, right? Because if you ask it like, can you make me a grocery list to do things, it will continue saying the same thing instead of actually doing the thing. And what you actually want is something which is aligned, something which can like solve things for you, solve tasks for you. And a simple way is collect a bunch of data set. And we talked about before how you can like, go hire people across the world, ask them to make some prompts, get some responses, like ask them to write responses. So you get like a supervised data set of input-output pair, and then you train the model. It's called supervised fine-tuning. In this case, you can have like make me a grocery list to do, cook a cheese toast, and the assistant and the data set could have, hey, this is the answer. And so again, the task is still next token prediction. We're still doing the next token prediction task. All we have changed is we don't do the next token prediction in the input. All of these losses will be masked. You don't like let the loss flow from these tokens, and all you do is next token prediction on this input. And then you add an additional token saying, hey, this is the end of sentence. So the model knows, hey, when it should stop saying anything. So moving from pre-training to post-training, the first step being SFT. First thing you need obviously some form of data set, right? At least you need some form of prompts. We can talk about how to get responses, but you need some prompts from somewhere. And what you're actually doing is you're modifying the weights for a pre-trained model to become a more assistant-like model. And then we talked about a second step called reinforcement learning from human feedback, where you don't have a static data set, where you let the model explore a lot, and we spent like lots of time talking about verifiable rewards, non-verifiable rewards right now. The normal case is this case where you mostly want to do human-like responses. Like in this case, you still want it to be assistant-like. We are not caring about math of code right now, and because you want to train using reinforcement learning, you want this notion of reward from somewhere. You want someone to give a reward, and ideally a human can give you a reward. Like if you have a human in the loop, it will be just terribly slow to train any model with human in loop all the time. And what we actually end up doing is we train a human proxy for the reward. So instead of getting reward from the human, we train this thing called reward model, which takes the input and output pair, and it will give you a score at the end of the day. It will give you a score of like, hey, how good this input output pair is. That way the model has an environment to play. It can generate different kind of responses, and because you have a human proxy here, reward model, it can try to increase, it can try to generate the kind of things which the reward model likes or the reward model prefers, because it can give you a higher score. And that is the entire pipeline we talked about. That is the reinforcement learning from human feedback, and it usually happens like you first do SFT and then you do RLHF. And we talked about a specific algorithm PPO before, which is actually used for RLHF. In practice, like when you actually see the paper, so first of all, what actually happens are many rounds of this. It's not a single round of like, hey, you have a pre-trained model, you do SFT, you do RLHF, and then you're done. In practice, both in Llama 2 and Llama 3, what they actually do is they collect a bunch of data. So it's prompt and some responses, and because you're also training a human proxy, right? You need a preference data from humans saying, hey, I like this, I don't like this. So you have humans in the loop, but it's in batch. It's in batch operation. You let the human collect the data. Maybe you spend have a day where on that day all the humans are giving you this preference data, and then you train your SFT model, and then you train your final RLHF model. But they want to keep increasing. They want to keep going through the loop. So in the Llama 2 paper, they mentioned they did this loop in a weekly basis. So each week they'll do this entire training, and maybe by the end of the week they'll go back, because now the model has improved, right? You have a better model now, which also means that your reward model will not be as good, because your reward model or the proxy for human is trained on a previous data or a bad model. So you actually have to go back to the drawing board, collect more preference data for humans, train this thing again, and come back and do this thing in loop. They did not mention in this paper what is the cadence for this thing, but they did mention it's trained for 6 iterations. So this thing happens for 6 iterations. And after each iteration, I'm sure they're going back to humans, collecting data in batch, coming back, training the reward model, NSFT, and the model again. Oh, also just to mention this, just to specify this again, we have a base model, which is a pre-trained model, and then you train this thing called the reward model, NSFT, right? It's still, your starting point is still your base model, because your base model still have all the information knowledge of the world, right? And you want to use that, you don't want to throw it away. So all these models are initialized from your starting pre-trained base model, because again, you want the thing giving you reward, you want it to be as good as your base model, the thing getting the reward. So the initialization for reward model is, so what you do in practice, you make a copy of your pre-trained model, and you change the final layer, which instead of giving a distribution over all the words, it gives you a single number, and then that is what becomes a reward model, and then you freeze it, because that this is trained on human preference data. You freeze it once, and then when you are actually doing the following steps, you have a freeze human proxy, because you don't want your human proxy to be trained in conjunction with what you're training for. Another thing very interesting is they actually train the reward model before the SFT model. Why is that? Because we use this idea from statistics called rejection sampling. The idea is very simple. The idea is that your reward model can tell you what are good things, what are bad things, right? It knows this response is good, this response is bad. What you can actually do is you can like generate a bunch of responses. Like you have prompts, you train reward model from human feedback, and you can generate a bunch of different responses, and you can throw away the bad responses and fine tune the model on good responses. I'll say this again. This is a bit unintuitive, because you generate responses from the Llama model itself, right? And you filter the data. So reward model just acts as a filter, like as a filter of what humans don't like, and then you're left with a bunch of generations from the Llama itself, which humans like, and then you fine tune the model back on its own generations. So it's like feeding like what you generated back to the same model. Why it actually ends up working in practice, at least for the SFT phase, is because both your okay, let's go back to the class where we talked about how base models, or these models, are like a bunch of simulations of all kind of entities which generate data. In this case, we are taking one kind of entity generating good data, and we're finding the model back on the good data. So that end up making like a model which can generate more of that kind, because it was already inside the model to, like, the model did have that distribution which can generate good assistant like data. You just needed to like somehow filter it, and like in this case, reward model acts as a way to do rejection sampling or like filter bad data, so it can be fine tuned on this good data set.
Do you say like how do you cut off stuff? And
Yes. Let's talk about that now. Okay, so post training is aligning model with human feedback. You get examples from human annotations, or you also generate synthetically. The backbone for all of this is still your language model that you started with. For reward model, okay, let's talk about specifically for reward model here. In this case, they have 4 different preferences. They have something called as really good, bad, and really bad. And they generate different, so they have a single prompt. They use 2 different checkpoints. I think this is in the next section, but they use 2 different checkpoints to increase diversity. So 2 different past Llama models are basically giving you 2 different responses for the same input. And then these 2 different responses go to humans. And the humans will be like, okay, which one do I like? And how much better do I like this one? Do I like it better, or do I like it really, really better? And then they also have a third phase where they let the human edit the response. They're like, oh, maybe if both of these are bad, or like you don't prefer something, maybe you can actually edit the response. So you also have edited feedback. And in this way, you actually end up getting, when the human actually chooses from one of these responses, you end up getting a clear ranking of like, was it edited, was it chosen, or was it rejected? And based on this 3 different categories, you can actually train the reward model, which will give you like the same score as before. Oh, another interesting idea here is that previously we talked about when we were doing reward modeling, is you can concatenate the input and output and pass it to the reward model. You'll get a score, use this loss function, get a score. In this paper, they actually, now because they have like 3 different kinds of responses, what they did was they concatenated the chosen response, the rejected response, and also if there was an edited response also in the same prompt. So you end up like having like all the 3 in the same thing. And they ended up shuffling the last 3, so the model cannot cheat. Like it cannot cheat. Oh, the chosen is always on the first position. So you have the prompt, and then you have 3 different kind of responses. At most 3 different kind of responses. And instead of like predicting a single number, you can predict 3 different numbers. You can predict it. Oh, for these 3 different inputs, is the first one chosen, or is it edited, or is it rejected? That way you end up like saving computational cost because you don't have to do 3 forward passes. You can like get away with 1 forward pass, which was also an interesting idea, right?
So how much data do you need to train one of these? How many labeled examples?
I don't remember, but we will come to it. Oh, it's considerably less stage, but yeah, I don't know exactly for RM how many examples are there. Yeah, so once you have RM, once you have your reward model, you can do the rejection sampling step, as in get prompts and get different responses and filter out the bad ones and train your model to say good things, basically. And that is a supervised fine-tuning step. You perform rejection sampling on human prompts, and you let so again in SFT stage, the objective is again very same as a pre-training stage. You're still predicting the next token. You're only doing that for the responses, not for the prompts, because you still want to be a next token predictor model. The only thing that has changed is the data on what you're trying to like predict the next token. And finally, DPO is an alternative algorithm to PPO. It's a much simpler version of PPO. And we talked about PPO before. How in RL setting you need a second stage where you want to train from human feedback, so the model can explore and like actually generate diverse responses. And yeah, they did a very similar a DPO stage as before. Oh, another actually very interesting thing I found. So now we have a pre-trained base model, right? So pre-training only happened once, right? Like you did the entire pre-training, and you have this final checkpoint. This paper has like hundreds of authors, right? I'm sure they're doing something, and a lot of that has to be done independently, right? A lot of this post-training work, a lot of evaluation, a lot of things have to be done independently. Like for example, let's talk about in post-training. Let's say you care about multilingual capabilities, and you also talk about code capabilities, right? And these 2 teams are separate. Like, how do you actually is one team working, waiting for the checkpoint from other different team before starting their work? Like, how does this actually happen in practice, right? Like, how do like many different capabilities, like for example, you want tool calling, you want like good coding agent, or you want like it to be really good in reasoning. One thing which is extremely surprising, and I'm still shocked at this, is model averaging works. What people literally do is you have these final checkpoints, and they take average in the weight space. This is very fascinating, and there is a lot of literature. Today I was talking to someone from DeepMind, and he shared a lot of literature to me, and he had some hypotheses about why this works. But this is extremely bizarre to me, because think about it, like you spend hundreds of millions of dollars to arrive at a checkpoint, and then you're fine-tuning, and in this high-dimensional 405 billion dimensional space, you arrive at a data point, right? And then you fine-tune and arrive at a different data point, and you just take an average. And that is better. Not only it works, it turns out if you have a multilingual checkpoint, and if you have a coding checkpoint, when you take an average, this thing can code in different languages. It's just fascinating how like model averaging is something which has like we stumbled upon it, and it really works. And like, so it turns out they do a lot of averaging across a lot of different things. I think I missed one thing. Even during the annealing phase, even during the end phase, they actually take a bunch of averages before you are like locking into the final checkpoint. Yeah, so
The models have to be very similar for that to work.
apparently not. So what I learned today is something happens at the so this result is apparently true across architectures, data set, even like if you're not doing language modeling, if you're doing vision, like CFAR, other things. What I learned today is something happens during the initial a few hundreds to thousands of steps is the model finds a convex space to go to, and so like in the first 10% of the training run, you take a checkpoint, and you then train 2 different runs, like shuffle the data, do other things, and you arrive at a final checkpoint, and you can average that, and it's the same convex landscape, and it works. So something happens in like very early on the training run, which sets or defines the final trajectory where it will land, and you can do checkpointing after that. Another result, for example, someone he also pointed this to me, that when you're actually training a model initially, let's say you're doing this post training, right? You have a starting point, and I think this was a result with clip models, which is like another image model. You have a starting point. This is a pre-trained model, and then you're training it like to be this final checkpoint, right? And you're optimizing it through the landscape, and you arrive at a final model. It has good evaluations. It turns out somewhere along this axis, you can do different kinds of weighting, right? Because you have a final checkpoint and you have an initial checkpoint, and you have many checkpoints along the way. You can take the average of your initial pre-trained model and your final model, and somewhere along this line, apparently you can linearly interpolate in the checkpoint space, and you'll get a better model than the final model that you arrived at. So model soup, model averaging, all of these works exist, where apparently in the weight space you can take averages, and not only that work, it can sometimes give you better results.
So like, how is there research on like how well that work compared to just training? Like, could you split 16 trillion tokens into 8 trillion,
And train independently?
and then just average them, or would it be just as good? Or
I don't know about that. All the work that I've seen is after pre-training. Like most of the work I've seen is once you have a pre-trained model, once you're like finding it for some stars. And in that regime, there are many. I think nowadays most frontier models, they always average across many different things. But that's a good question. I don't know during pre-training how that would work. But if that would work, that would be very interesting.
How many weights are there? Like, what is the matrix?
So, I mean, we know the number of parameters, which is like 405 billion.
Yeah.
And so there are like 405 billion weights.
Oh.
And then, like that is the dimension space we are in.
Oh.
So like imagine a 405 dimension
And you're
space.
just taking average.
Yeah, and this is one point. Like your final model is one point in that 405 dimension space, and you can have different checkpoints, and you're taking averages in that space.
So, like, what is the intuition behind it working for, let's say, code and for a different language, and you're taking an average and it is working better?
I have no clue. I don't know why it will work across different tasks,
Yeah.
but from what I just learned briefly today was his thing was that somehow very early on you decide a direction and you decide what kind of this is a highly non-convex space, right? But you somehow end up in a similar convex space, and in that space averaging works. I don't know why. I still don't understand why it would be better than either of the two, but apparently it is in many cases.
Apparently there's a shared value in the context space and like representation space. At least someone said that.
Okay. For another dimension, like this is our another dimension. Yeah.
It's just in a representation space, like all these low losses have like a value sort of that we can just generalize. And taking an average sort of just empirically does it.
Maybe it's also somewhat related to this plot. Not exactly, but like it can somehow point out that how different models have similar validation laws. I mean, obviously it says nothing about that high dimensional space and like what's happening, but clearly like once you are in a large enough model regime, you do get like some robustness to where you are, which means that all the perturbations along that model, because okay, imagine taking average is a perturbation, right? Like you're actually changing numbers. My a priori assumption would be even if you change one floating point of like number, everything should not work. But it turns out your Adam or something like gives you a final data point which is robust to perturbations, or at least to average perturbations in that thing. Maybe people should try small perturbations and see if that works.
Yeah, I guess like one intuition that might be helpful is here the number of parameters is still like a lot less than the number of tokens. So either you're like super over parameterized or like this is kind of under parameterized, right? Like you have only 405 billion parameters and like 15 trillion tokens or something. So you have some sort of best fit. Like imagine you like fit a line to a bunch of points, but the line only has two parameters, right? Like if
So-
you move a point a bit,
I see.
the line would not bigger that much.
So we are like in underfitting regime in some ways.
Yeah. It would make it more robust.
Sorry, do you also think it's because attention is actually very sparse? So when you take linear average, some of them the zeros just turn into bits and then stuff. Do I make sense?
You do make sense, but the attention operation is on keys and values, which is being produced by the matrices that we are talking about. So we are like modifying the matrices which produce these keys and values. And like if the matrices are different, my assumption would be these keys and values will be very different, but somehow the results don't change. So it's just very bizarre that this is true. But this is really good for like people, like for the teams training frontier models, because then they can independently actually do different kinds of research and like they can actually average things and it ends up working. Right, so we talked about the data. Okay, so let's talk a bit more about like how this, like how did we get different kinds of data? Okay, because like in SFT phase, right? In here, we have one prompt and we have several different responses being generated by different checkpoints of the model. So this is a synthetic data and this is a synthetic data generated by the model itself, right? And all the fine tuning will happen on synthetic data. Even though the preference data is coming from human, that is the only thing coming from human in this pipeline. The actual generated responses is from the model. So if you think about it, like if you have bad data coming out of the Llama model, the entire thing becomes garbage out, garbage in, because you generate something really bad, you train it back on it, and you do this for 6 times, you'll end up, like this could very easily degenerate, right? So one thing that they talk about is like how to ensure the quality of the synthetic data being generated, or like the data quality control is very important in the post-training stage especially. They mention things like, they notice the initial checkpoints have higher, like a lot of emojis, a lot of exclamation points, which is again probably an artifact of how the reward model is trained, because the reward model probably prefers this. Or they have like it's highly I am sorry, I apologize kind of a thing, overly and they have to like remove these things in the data cleaning thing. They had to do topic classification for different math problems, because later they talk about how the final model was good at some math skills and bad at some other math skills. So it had to like find, like get some topics on like which math skills it is bad at, and like add that kind of classes. They also did quality scoring for each data point. They use 2 different ways to like score the quality of each response. One of them we know is RM, right? We are using the RM model to actually get a quality of the response. But they also use a previous Llama checkpoint. They use a previous Llama3 checkpoint to use model as a judge. So in this case, you're not like changing the model to be a reward model or anything. You just have a Llama model, which can basically tell you how good the quality of something is, right? So they use both of these criteria. In this case, they use RM, a reward model specifically trained to tell you how good something is, but also just a previous Llama3 checkpoint to tell you, hey, is this a good quality thing or not? And they notice high disagreement rates. They notice like RM based thing and previous Llama based things actually have high disagreement rates. And when you combine both of these things together, you get like high recall. But they say ultimately they ended up using an OR condition. So if either of them thinks it's a high quality thing, maybe they're like seeing different kinds of quality. They end up like filtering based on this as well. And because you are going for 6 rounds, you need to somehow also ensure that the difficulties the difficulty of things is challenging over time in the next round as compared to previous rounds. So they also did some form of difficulty scoring for each problem statement. And a lot of deduplication is like throughout the entire pipeline, a lot of deduplication. So both the model doesn't memorize stuff and it doesn't get good at like some small forms of things. Next, in this, like continuing on the post training, there's a lot of information which goes into like making this checkpoint really good for different kinds of tasks. I have alluded to like already to code, math, reasoning, hallucination, multilingual, long context. So now we have like 5 different sections of like, again, this is, as I mentioned before, this is primarily a data paper. Everything we talked about this until this point was pre-training, but for post-training they talk a lot about how to curate the dataset for different kind of tasks. So at a high level, the strategy is very simple. You take a checkpoint, you take a previous checkpoint that you had during pre-training, and then you start modifying it for one capability. Be it code, be it reasoning, be it multilingual. And they call this thing code experts. So they call these things like experts. In this case, this is a code expert. So this is accomplished by branching the main pre-training run and then continuing to pre-train on some data quality. So because they want the model to be really good at like some tasks, they will stop the take a previous pre-training checkpoint, and for the last 1 trillion tokens, you keep this mostly of a code data input. Also for code, they mentioned that once you have Llama 405B, the synthetic data from 405B would be really helpful for 8B and 770B models because you're getting a superior data set, but it is not helpful for the 405B itself, especially the code data set, and it can sometimes also degrade performance. To actually solve this thing, especially for code, they care about execution feedback, because if you have a code data set, you can actually execute it. And this comes back to we talked about verifiable feedbacks, and code is one of them. Again, a lot of synthetic data going on here. They generate problem statements, they generate solutions, like in code space. Once they have solutions, they do some type checking, so it doesn't have syntax error. But they also generate unit test cases. So problems are generated, solutions are being generated, unit tests are being generated to like verify if the solution is correct. And if there are errors, they actually let the model change the problem, but they also let it change the unit test case, which I was very surprised about.
So why do you use
Delete them.
Yeah, so I'm sure like we have seen Sonnet 3.7 doing sneaky things like removing our unit test cases, and yeah, this is probably like some of how this happens. But yeah, there's something which was very surprising. They let it change the unit test cases when things don't work. Oh, another thing being internet is dominated by Python or C++. Like GitHub has a lot more Python, C++ than other lesser known languages. So they use previous checkpoints to also like translate to other programming languages, lesser known programming languages. So you can also like do fine tuning on different synthetic data from themselves. They also use a technique called back translation. This is very common in translation literature. At a high level, the idea of back translation is you have an input source, you go to a target domain, let's say English to French, and then you train a reverse model to go from French to English, and then you can basically evaluate how good your starting point is, because you have a ground truth for starting point, which is English. You can do that for code. You can start from a code snippet, ask it to summarize the code or write a docstring, and from docstring artists to write the code back, and use a different LLM as judge or something to evaluate were you able to come back to the same starting point. This idea is called back translation. This is very common in translation literature and also in code generation literature. So yeah, they can synthetically generate this kind of data set. Like you can take like code snippets from the internet, ask it to like write docstrings or write summaries, and then back translate and just see is the model able to get to the right translation? If not, can we like fix it? Can we improve it? And a very similar story goes for multilingual as well. They noticed that most of the data is English on the internet, so you need other mixtures. They did a very similar thing. They branch off the pre-training run, continuing pre-training on a data mix, but this time you have like 90% multilingual tokens. That way you have an expert which is a multilingual expert. And again, like you need a lot of like other kind of sources. So NLP had a lot of benchmarks from the past, mostly in English, but you can like translate it to a different language, remove some low quality data set, and also like because a lot of this is now chat, you have to take benchmarks and like convert them into chat formats. So yeah, they rewrote like the benchmarks in like dialogue settings, so it's a dialogue, multi-conversation dialogue setting. Something interesting they notice is there's this phenomena I learned called translationese, which is, and this is true for both machine generated translation and human generated translation. Even when humans like translate from one language to another, there are some artifacts in how humans translate, which is very different if you had to write that in the original language. And because most of our systems are trained using human translations, this artifact is also present in machine translation. As in like there are artifacts in like you can identify, hey, this is a translation and not written in the original language. Also, if you use, so okay, the point being they do not use translation data, like so they use translation in code, but they don't use translation in multilingual setting, because this will both add the artifact but also add the cultural and gender biases of the source language, and you don't want that, like because in a different culture the norms, the biases could be very different, and you do not want to like carry over the biases from English language to other languages. Having said that, they do use translation for math and reasoning tasks, because for math and reasoning tasks you can like it's much more structured, and like translation doesn't get back to you. Yep, so very similar story going on for translation, and it goes on and on again, like similar things happen for math and reasoning. I don't have a lot of time, so I'll probably skip a lot of these things. Oh, okay, this was interesting. We talked about long context before, but there was no mention of data set for pre-training. For post-training, they mentioned 3 very interesting ways to make the data set. So now if you remember, like we are here, right? We eventually ended up at a 128K context window, but for the most part of the training, these checkpoints are at 8K context window. So what they did was they used these checkpoints, like the 8K context window checkpoints, to generate data which could be used for longer context. Three different examples. The first one is question answering. You can actually take like a large Wikipedia page and take a small paragraph from it, ask some question based on this paragraph, and your 8K model can do that, right? 8K context window model can take a small paragraph and answer question based on that, and then you throw in the entire Wikipedia page for the long context training, and then ask the same question and the answer is in there because it's in the context. That is one way they train for question answering. For summarization, they do hierarchical summarization. You have 8K context window. Let's say for Wikipedia, you break it into like 4 different chunks, independently summarize each of them, and then summarize each of them again. So you have a summary answer for long context, then you throw in the entire Wikipedia page, and then you have a ground truth summary. You can do that. For code, they did something interesting. They parsed all the Python files. They found the import statements coming from different files. So you can like see which files are being imported here, which are dependencies. And from some of the most commonly used files that is being referenced, you can actually remove some files. You can both like remove some files and prompt the model to like find the missing file, which should be present here, and also like generate the code of the missing file. So in a way, they're trying to like take code repositories and create large and this is probably because this is also how we would eventually use it. Like we want it to be used in like multi-file setting, and like you would probably want the model to like fill in some code gaps. So that is how they create long context code reasoning information. Another interesting point they mentioned is that only adding like a very small. Another problem with like long context fine tuning is that you still don't want to lose performance on like short windows, right? So you cannot like just throw in like suddenly like long context information, because you still want to ensure it works on the short context window. They noticed that even adding a very small synthetic generated data, like as simple as 0.1%, it retains the performance on short context, but however still optimizing for long context, which just says that even like if you let the model see information for even a very short amount of time with short amount of synthetic data, it can be really good. And this is probably also shown by this figure, how at the very end you start increasing the context window of the model. one more thing I have mentioned this before is hallucinations. We talked about how in SFT lecture how models hallucinate. They hallucinate because in SFT you are like showing it question answer responses, and some of these the model might not be aware of during pre-training, and you don't want the model to lie, right? You don't want the model to like say false things that it was not aware of before. And we have talked about how you can like get around it. Like you want to know what the model is aware of during pre-training. You don't want to like because it's very hard for it to learn new language during SFT. And what you do is like, again you get a Wikipedia paragraph, you generate a question and a response based on this paragraph, and then throw away the paragraph and just ask the question and see if the model can come up with the right answer. If you like do it 5 times and if it comes up with the right answer 5 times, that means the model is aware of the right answer. But if it is hallucinating, that means that it doesn't know the right answer, and it's making stuff up. And in those cases, you say, hey, I don't know that. Like you let the model say, I don't know to those answers. In that way, because the model is aware of what it does not know, but you don't want to force it to say wrong things or like hallucinate information. In this way, you can like train the model to say, hey, I don't know the answer to this question because you know what the information is going there. Are there any questions at this point? I said a lot of things and.
I have one question about the RM. Like the model will be as good as the RM as good as we are
Yes,
getting the result.
yes,
So
yes.
how are we quality testing?
The RM. So people have RM benchmarks, and that is a very good question. Like because the RM, the model cannot be better than the RM because RM is your proxy, right? People have benchmarks for how good the RM is, as in like, does your RM has biases? Does your RM like say give high scores to like good things? But at the end of the day, in this setting, the eventual benchmark is when you train with RM, is your model like what is the performance of the model? And also like because you're doing it in a loop, you actually go back and like improve the RM based on like, because imagine your model has become better, your RM has not become better, so they both have to level up together. So that is why you have a loop where you go back, collect preference data, and like improve the RM on this newer checkpoint, which is like more.
So is the human in the loop anywhere?
The human in the loop is just to give you data for preference model. And I'm sure like I'm not looked into RM evaluation, but I'm sure RM evaluation is similar to like, okay, you get this preference data. Now is the RM like how good it is, like is it reflecting those preferences? And maybe people also do like independent human testing on the RM itself. But yeah, there's this thing called RM bench. They try to like evaluate RM on different axes, like biases, etc., and they see like different RMs are very different based on like the kind of data is coming.
So is the RM like a bench for like all the different models?
For all the different RM models.
For all the
Yeah.
different
Because different RMs will be biased in different ways. In the last 2 minutes, I just really want to quickly touch upon the image, how you actually modify. There's a lot going on here, but at a very simple level, we know that the transformers can take in discrete input. So we know like transformers take text, right? Text is discrete. Text can be broken down into tokens, and each token you can have an embedding which can be passed to text. Images, audio, video, all of this is continuous inputs, right? So you have to somehow find a way to like make it discrete, and there can be like different solutions, right? Like you can imagine like taking an image and like somehow discretizing it to pass it to the model. Also, like let's say a typical image is like 256 cross 256 tokens. A very simple way that you do in practice is called vision transformer. What you actually do is you just break that into chunks, like break that into small patches, and treat and then linearize the patch. So like basically like do this, make them into like a 1D sequence. So you're taking a 2D sequence, making it a 1D sequence, which means you still have to like somehow keep the positional embedding because that is really important for it. And all you do is like apply a single neural network on top of it, which is called linear projection, to get an embedding. And that is how you like take a continuous variable, break it into batches, get a single embedding, and like make it discrete. And once you have that, everything on top of it remains the same. Like the transformer, everything else can now operate on this embedding space.
So like what kind of vocabulary size
There's no vocabulary size here because your vocabulary is purely defined on the go. Like this initial neural network defines like what its vocabulary is. There is a lot more to cover for this, but I think we are out of time, and there are people waiting for the place this time. There's an event right after this, so I think we can continue next time. But thank you so much. Thank you everyone.
Three things